Okay, good morning. Let's look at examples for Thevenin and Norton today. Again, an important topic for the final exam. So I'll try and get through two examples. And the third one, I'm going to record a video and post it online. And so then you can review it after class. Okay, so section 3. Okay. All right. So problem statement, determine the Thevenin equivalent resistance between terminals A and B. So if the question or the problem statement specifically references a set of terminals, then we do not make any modifications to the circuit. We simply begin our analysis by looking into those terminals. So in this case, it tells us terminals A and B. Oh, that's rainbow colored. Let's take that out. All right. Which is right here. Okay, terminals A and B. So we want to find REQ. REQ between these terminals, and we have to look into the circuit from the perspective of REQ. Now, first thing as always is to set up the problem correctly, because if the problem setup is incorrect, then everything else that follows is going to be incorrect. So let's okay. RTH is the question mark. What do we do to find equivalent resistance? We need to get rid of all the sources in the circuit so that the only thing left in the circuit are resistors. And once you have resistances in there, you can simply analyze and reduce it down to one single resistance. So not replace, reduce all independent sources to 0, meaning replace our voltage sources with a short circuit and all current sources with an open circuit. Remember, this is just to find the Thevenin resistance, okay? In order to find the resistance, we have to remove all the sources from the circuit and redraw that circuit. Because every voltage source replaced with a short, every current source replaced with an open is going to change our circuit diagram. Right, so let's redraw it. I have V1 on the left, replaced with a short circuit. R1, R3, now I'm drawing these out, but this is again just for explanation purposes. Since this is the first example, you do not have to draw out these dots and mark the place. Okay, I'm simply marking the place where the sources were connected, but you don't have to do that. And I will show you in the next step or in the next circuit diagram what you actually have to show. And I1 is open. And another short for V3. And then R4. And then I2. Let's see, V1, V2, V3, R1, R2, R3, and R4, and I1 and I2. All right, so all components are included and covered. REQ between these terminals A and B. Let's take a pause while you write it down and think over it. Only independent sources can be reduced to 0. Voltage sources replaced with a short. So you got V1, V2, V3, all replaced with a short circuit wire. And then current sources replaced with an open circuit. And so you have two opens, I1 and I2. Yes. No. I can give you one if you want one, but it just makes it a little complex. And that's a good point. The reason I teach 3 separate techniques in my class, but IN separately, RTH separately, and VTH separately. The reason we need to learn all 3 analysis, the reason we need to learn how to find all 3 quantities is because all circuits are not reducible, right? You can only reduce a resistive network to one single resistance if you can reduce it manually. Measurement, yes, measurement is easy. You just take your multimeter, put it across the terminals, and just measure. Doesn't matter how the circuit is connected, it will be able to measure the resistance. But if you wish to perform a theoretical calculation, you need resistors connected in series or parallel. Sometimes the connections are neither series nor parallel, and you cannot reduce a circuit. The examples, obviously, if I choose an example in this class, none of the examples have irreducible circuits. Every circuit in this class is reducible, but in real life, it doesn't work that way. So you would not be able to reduce a circuit to find RTH. So you need to find VTH first, then you find IN, then you apply Ohm's law, and then you find RTH that way. That is one of the reasons. And then the question was asked about dependent sources. That's another reason. If you have a dependent source in there, you cannot reduce a dependent source to 0. You can only reduce independent sources. Remember, the circular ones to 0. A dependent source, which is the diamond-shaped ones, they cannot be reduced to 0. So in that case, we again need to find Norton current, Thevenin voltage, and apply Ohm's law to find RTH. All right, but any questions about this? Straightforward enough, right? So what you actually need to draw is this. Again, this I was just drawing for explanation purposes or teaching purposes, but the actual circuit looks like this. And then B, and that's it. That's what the circuit looks like for REQ. Watched that. Okay, REQ. And this is R1, R1, R2, R3, and R4. So this circuit, the second one, is all you need to show. You can show the first one too. That's fine. But the second one is more important. Either one. Okay, either one. So what do we see? Think back to the beginning of chapter 2. When we wish to find REQ, we start at the farthest end from REQ and move towards our terminals, reducing each resistor one by one. So the farthest end from REQ, the resistor we have is R1. We move towards A and B. What do we see? R1, the next resistor up is R2. Relationship between R1 and R2, they are absolutely in parallel because of the short of V1. R1 is now connected at both ends to R2. So I can write the equation for REQ as R1 in parallel with R2. Then next up is R3, parallel or series. So it's in series with R3. And then final one is R4, which is in, again, in parallel with the rest of the combination. So I don't have any values here just because I wanted to explain the concept. But if there were values at this point, you simply plug it in from your calculation. That Req is your Thevenin resistance for that circuit. Okay. I will also draw it out with the other method I had explained, which is you have A and B. Let's draw it out this way. If we start from A and B, the first thing is I have R4 between A and B. I'll wait. Let's finish this. Any questions about this? Okay, straightforward enough. So this is just the other technique that I use to find Req. You have R4 connected between A and B. Then we have R3 also connected to A. R3 is connected to R1 and R2. I'm going to split. I have R1 and I have R2. And the other end of R2 is directly connected to B. I'll just touch down there. And the other end of R1 is also connected to B. So touch down there. And then this circuit on the left clearly shows that R1 is in parallel with R2, which is in series with R3. And that entire branch is in parallel with R4. All right, let's take a 10-second pause. Let me know if you have any questions. I wish they had bigger screens rather than just like the curved monitors. That would help a lot. But any questions? Straightforward, right? And again, of course, it's straightforward just because of the way the circuit is. Real life circuits are not this easy, right? Unless you break it down into multiple pieces. So let's move into the next example. Find the Thevenin and Norton equivalent circuits. And this is important. If the 2 ohm resistor is the load resistance or represents the load. Okay. And I will take you back to the first point in the 2 summary slides. Oh, we went too far back. The first point, the summary slides, determine the Thevenin and Norton equivalent circuits as seen by a particular component, or as seen by would be the same as a component is the load component. Load or also any of these excuse me. Any of these three phrases mean exactly the same thing. So again, if the problem statement has as seen by particular component, whether that component is a source, a resistor, capacitor, does not matter. If you see the phrase as seen by, or the phrase represents the load or represents the second circuit, that component is not part of your analysis. This is very important to understand. If you see these words, then you remove that component from your analysis. It is not part of that circuit. Remember the example that I used when introducing this topic was of this circuit, right? R6. I said, what if you wanted to find a value for R6? Then we remove R6 from our analysis and we determine the rest, or we analyze the rest of the circuit and we find the Thevenin and Norton equivalent circuits. So again, if the problem statement has any of these three phrases or words, then you remove that component and it is not part of your analysis. And so we come to example 2 and example 2, the 2 ohm resistor represents the load resistance for network 1. So we remove that from our analysis and our circuit is or looks like this. This is 12 ohms, 4 ohms, 6 ohms, and terminals A and B. And that's it. This is the circuit we need to analyze 3 times in order to find the 3 quantities. We redraw it 3 times. Okay. Once for resistance, once for voltage, once for current. So let's begin. RTH, we reduce all independent sources to 0. There is only one source in the circuit, 30 ohm source, 30 volt source. And so that is replaced with a short circuit. $12, 4, and 6. What is my REQ? Between A and B. Yes. 12 in parallel with 6, which would be in series with 4. And so we solve for that and we get 8 ohms. So my REQ (12 parallel with 6 plus series with 4 ohms). 12 parallel with 6 should give me 72 divided by 18 plus 4, which is equal to 8 ohms. So my Thevenin resistance, RTH, which is equal to REQ, is 8 ohms. All right, 10-second pause. Original circuit with 2 ohms removed. Then you perform 3 separate analyses on that circuit The first one, RTH, reduce the independent source to 0. In this case, the only independent source is the 30-volt source. Replace it with a short circuit. That short circuit causes the 12-ohm resistor to come in parallel or be connected in parallel with a 6-ohm resistor. So 12 parallel with 6 gives me 4 ohms, which is then in series with the 4-ohm resistor between the terminals A and B. And hence Req is 8 ohms. So the Thevenin resistance for this circuit is 8 ohms. All right, questions? Calculations can come later, but understand the steps. Yes. So this is, students don't have to draw. So the question being asked is about the voltage source and the 2-ohm resistor. This is for explanation purposes. Okay, this is for explanation purposes. Students do not have to draw this when they are, when they're presenting their work. Okay, this is for explanation purposes. So students understand not to take the 2-ohm resistance into account. You can directly go from this circuit and draw RTH and then, VTH and IN. Does that answer your question? Okay. And this is also how most books will have the analysis. You simply take the original circuit, redraw it for RTH, and not show the 2-ohm resistor. But does it make sense? Right? Again, these are just the steps that I'm showing for explanation purposes. RTH without the 2-ohm resistor and without the voltage source. Okay, now that we have RTH, we forget about this. We don't need it at all. Not until the very end. Okay. RTH has no bearing on VOC and has no bearing on IN. So we now redraw the circuit to determine the Thevenin voltage. Obviously, there will not be any voltage or any current without the source being in the circuit. And so logically, if you perform an analysis for VOC with this circuit for RTH, voltage and current would be equal to 0. There's no sources. All right, so 30 volts. This circuit brings up an important concept of circuit analysis. So we have A, B. Remember, convention is to take plus at the top, minus at the bottom. At the end of your analysis, if it turns out you have a negative value, all you do is you flip the signs. That's all. So plus minus VOC between terminals A and B. Before we begin analysis, I'm going to do one more thing. I'm going to draw out this current, and I'm going to call this current as, let's call this IL, just to keep it different from all other notations. So the concept here is the 4-ohm resistor, or the concept applies to the 4-ohm resistor. What do we see? We are performing analysis. Obviously, the 2-ohm resistor is not part of the analysis. So because of the absence of the 2-ohm resistor, the 4-ohm resistor is not connected to anything. Again, remember, we are analyzing the open circuit voltage. The terminals have to be open, right? The terminals are open, and IL is coming through, is being supplied by the 30-volt source. It is flowing through 12. That should be ohms. the 12 ohm resistor once it reaches that junction point, where is it going? Current needs a pathway to flow through. 4 ohm resistor is a dead end street. Is any current flowing through that open pathway? No. So none of the current is supplied by the voltage source is going to the 4 ohm resistor. All of that current is going down here to the 6 ohm resistor. And this is the concept where you have 3 resistors connected together at that node, but one end of one resistor is left hanging in the air. It is not connected to anything. If it's not connected to anything, the current flowing through that pathway is 0. If the current flowing through that path is 0, then the voltage at both ends of that resistor is exactly the same. And so we can say that point A has the same voltage as that point. And then if you want to find the voltage across, voltage between A and B would be the same voltage as voltage across that 6 ohm resistor. And so in this case, the concept leads us to conclude that the 12 and the 6 ohm resistor are in series, because the third connection, which is the 4 ohm resistor, is not connected to anything. Taking that concept further, you could have hundreds of resistors connected at same junction point, but if those resistors are not connected to anything, they're all open circuit. They have no impact on that other circuit or the rest of the circuit whatsoever. Okay, so let's take a 10-second pause. Think over that. Let me know if you have any questions. Does that make sense? I could redraw the circuit, and I could redraw it this way. Oh, come on. So 30-volt source plus minus 30 volts. 12 ohm, and then 6 ohm resistor. The 4 ohms is connected there, but again, has no impact on the circuit whatsoever. Plus minus here is exactly the same as plus minus here, because it has the exact same potential. And I have current IL flowing through the circuit. So now we have established that the open circuit voltage is the voltage across the 6 ohm resistor. Now you simply choose which techniques you wish to apply. I have 2 resistors in series. What happens to voltage in a series connection? It gets split, it gets divided. Voltage is divided, so I could apply voltage division. Or you could apply Ohm's law twice and find the current IL the first time, and then you apply Ohm's law again to find the voltage across the 6 ohm resistor. Or apply voltage division, one-step answer. So if I apply voltage division, I can simply write VOC is a fraction of 30 volts. The fraction is given by 6 divided by 12 plus 6 REQ for that series network. And therefore VOC is equal to 6 over 18 1/3, which is 10 volts. And then therefore my Thevenin voltage is also 10 volts. Once you set up your circuit, then the analysis technique is different. So you choose which technique you wish to apply. Okay. The setup of the problem is the most important. Yes. Because the 4 ohm resistor is not connected to anything, then no current is flowing through that pathway. So 30 volt source is supplying current IL. IL goes to the 12 ohm resistor, comes to the junction right there. And when it comes to this junction right here, 4 ohm is a dead end street. No current would flow through there. If no current is flowing through there, then I is 0. Voltage across those 2 points is equal to 0. It's the exact same voltage at both ends of that resistor. And that's why we can not move, but we can measure the voltage at the other end of the resistor, and it would be exactly the same. Because current flowing through there is 0. And we can do this exact measurement in a lab on a physical resistance circuit, and you would see that it will work. Because there's no current pathway flowing through there. It has potential. Remember, voltage is potential difference. So it has potential, but there's no current pathway. All right, any other questions? Okay, then let's move on to Norton current, IN. Norton current, again, is different from the Thevenin voltage. .30 volt source, 12 ohm resistance, 6 and 4. And this time, the modification is that the 2 ohm resistor originally, which is supposed to represent the load, is now replaced with a short circuit. Current needs a pathway to flow through. So if I'm analyzing for Norton current, I need to have a wire or a short circuit between those two terminals, ISC, short circuit current. And my terminals of analysis are still the same. We have A and we have B. Everybody understands setting up of the circuit? ISC. So now our job is to calculate ISC. The analysis technique we choose just depends on the circuit layout and our individual choice. But what do we see? In the first case, well, not first case, in the case for the Thevenin voltage, the 4 ohm resistor was not part of the circuit. However, now it is because of the applied short between A and B. And the short circuit wire between A and B causes the 4 ohm resistor to be connected in parallel with the 6 ohm resistor. Again, the short circuit wire causes the 4 ohm resistor to be connected in parallel with the 6 ohm resistor. And I can redraw the circuit in this manner. Six, 4, and this is 12. This time I'm going to label, let's see, label this current as, I don't know, IZ. IZ is coming down, and then it splits. Some of it goes down here, some of it goes down here. Think over the two circuits, right? We have a short circuit between A and B to analyze ISC. That is the setup that is required for Norton circuit analysis, okay? And what follows after that? Well, that depends on how you visualize the circuit. So we look at the circuit, and I can see that the short circuit wire is causing the 4 ohm resistor to be in parallel with the 6 ohm resistance. And so I am redrawing the circuit in a way that makes sense to me. You can redraw the circuit as many times as you want until it starts making sense to you. That's always my strong advice to students. Do not skip steps and always redraw the circuit as many times as you need. So I have a 12 ohm resistor in series with a parallel combination of 6 and 4. One more important point, if we extend ISC here, if I extend it backwards, what do we see? What do we see? Absolutely. ISC, the current that we need to find, is the current that is flowing through that 4 ohm resistor. Does everybody see that? Right? So again, take it step by step. Do not just be in a rush, because when you're in a rush, that's when errors happen. When you take it step by step, we extend ISC, we can see that it is the current that is flowing through that 4 ohm resistor. Yes. Your question? Okay. All right. So IZ is the total current being supplied by the 30-volt source. It flows through the 12 ohm resistor. When it gets to that junction, it splits. A part of it goes down 6 ohms, the other part goes down 4 ohms. And that current ISC is what we need to find. So again, multiple ways to do this. We can do a repeated application of Ohm's law, reduce all 3 resistors down to one single resistance, find the total voltage, sorry, not total voltage, total current. Once you find the total current, you can find the voltage across the 6 and 4 ohm resistances, or you can directly apply current division. And I'll show you both. Okay. Since it is the 6 and 4 ohm resistors that are in parallel, I can describe the voltage across both of them as VZ. Right? Voltage across parallel connections remain the same. So this would be plus minus here and plus minus here. Parallel, so the same voltage. I can apply voltage division and find VZ. So let's do that. First, I'm going to reduce 6 and 4 into one single resistance. Let's do it here. So from here, I'm going here. 6 in parallel with 4 gives me 24 divided by 10, 2.4 ohms. So VZ is the voltage across that 2.4 ohm resistor. And VZ can simply be given as a fraction of 30 volts times 2.4 divided by 2.4 plus 12 from voltage division. And this is, what is this? 2.4 divided by 14.4 times 30. Five volts. Oh, even before that, side step. We had VTH as 10 volts and we found RTH as 8. If you apply Ohm's law, what do we expect our answer to be for Norton current? V equals IR. What is I? 10 divided by 8, 1.25 amps. But here's the point. What if one of our answers was incorrect? If either the 10 volt or the 8 ohm answer was incorrect, then the third quantity, if you have tried to apply the shortcut and we're trying to find the third quantity, that would also be incorrect. That is another reason why we need to be able to analyze all three quantities independently. But in this case, it allows us to predict or at least know what our answer would be. So if we apply voltage division, we have VZ, therefore ISC is simply equal to 5 divided by the 4 ohm resistor, which is 1.25 amps, which is what we expect. 1.25 amps. Make sense, right? Now let's do it with a slightly harder way. Yes. Well, we can, but there's no reason to do so. It will. In real life, yes, we would. We would want to verify it with multiple methods and multiple ways to ensure that our answer is absolutely correct. That's a good point. We can use multiple ways to actually verify our answer. And so I'm going to verify my answer by applying current division, series parallel analysis. So if I wish to find IZ, I could reduce the entire circuit down to one single resistance. And my total REQ in this case would be 12 plus 2.4, which is 14.4 ohms. So my total IZ is 30 divided by 14.4, which gives me, I think it is 2.0833. Amps. And then if I wish to apply current division, I can find the answer by writing out this equation. ISC would be a fraction of IZ, so 2.0833 times my REQ for 6 and 4. Remember, current division is only being applied here. Total current comes through 12 ohm resistor, and then it gets divided between 6 and 4. So the only resistors in play are 6 and 4. REQ for 6 and 4 is 2.4 ohms divided by the 4 ohm resistor, which again gives us 5 divided by 4. 1.25 amps. Two different methods, but the exact same answer. So again, in real life, if I was doing this for a particular application, absolutely yes, would check my answer by applying multiple different analysis techniques. Okay, there is no other way to verify this, especially theoretical calculations. You apply multiple ways to solve the same problem and see if you get the same answer every time. That's why I always also tell students, like a solved example in class, whether it's for mesh current or superposition or node voltage, you practice it multiple times with all three methods because you already know the answer. So you practice and practice and practice again and see if you can arrive at the right answer or not. Okay. So in this case, these are the only two methods I can see. You reduce it down to one single resistance, apply Ohm's law, find the current, IZ, and then apply current division. You could also, well, current division is a shortcut. Once you have IZ times 2.4 gives you VZ, just 5 volts. And current division, again, is just allows you to skip one step. Make sense? Right? So Norton current is 1.25 amps. Our job is not yet done. We still need to draw out our circuits. So my Thevenin circuit looks like this. I have a voltage source in series with a resistance. Voltage source is VTH, which was 10 volts. Resistance is RTH, which was 8 ohms. And terminals A and B had the 2 ohm resistor connected in series. I'm going to note this as A and B. And in the original problem, this was given as Vx. That's the Thevenin network, voltage source in series with the resistance. And then the Norton network, the Norton circuit, has a current source in parallel with a resistance. Note the current direction and the voltage polarity. Okay. The current direction will go up top because the component current is going down. Remember, ISC goes down. That's the original polarity that we took. Okay, so IN here is 1.25 amps going up, which corresponds to the plus and minus sign for Thevenin voltage. Okay. Otherwise, our equations would never balance out. And this is RTH, which again is 8 ohms. And then our 2 ohm resistor connected here. Yes. Which are N? The Thevenin resistance. Oh, you're talking about this short. Yes, that is only to find Norton current. That's it. Yeah. That's nothing else. And that short, again, the original problem statement was to find the Thevenin and Norton as represented by 2 ohm resistor, right? So we place a short in place of the 2 ohm resistor to find Norton current. And when you want to find Thevenin voltage, we simply remove the 2. It should be open terminals. But once we finally have our circuits, we connect the 2 ohm resistances back into the circuit, and that is our final answer. At this point, if I wished to find Vx, it would simply be voltage division, VTH times 2 divided by 8 plus 2, which gives me 2 volts. That 2 ohm resistor could change to 10 ohms. I could still find the voltage Vx, one-step answer, right? Same thing with the current flowing through the 2 ohm resistor right there. Okay, so we'll end class here today. What I'm going to do for example 3 is I'm going to record a video either today or tomorrow morning and post it by tomorrow afternoon. I hope to do it by today afternoon itself. And then you'd have examples 1, 2, and 3 to review. The homework is due this Friday, but I'll push it back to Sunday because it has more problems than superposition. And then, of course, quiz as usual on Monday will be on Thevenin Norton. Okay, I'll be available for questions all day today, tomorrow, and Friday over the weekend. And so I want to make sure everybody does a good job on Monday. All right. So I'll bid you goodbye, and I will see you all on Friday.